For the last problem in chapter 23, we have a electric potential function given in terms of V, and the variable, independent variable, is Z. We've seen an example of this when we calculated the electric field for different configurations using Gauss's law. Because there's a restorative relationship between the electric potential and work, there is also what is known as a conservative force acting in the electric potential. So the electric force that we can calculate is also known as a conservative or restorative force, which means that the electric field can be easily obtained by taking the partial derivative with respect to Z of the potential force, potential field. Sorry. And if we do that, then this is the partial with respect to Z. That means treat Z as your only variable and nothing else. So if we write our function down and take derivatives of this, notice that the sigma 2 and epsilon naught are constants, so they come out. I get a minus sigma over 2 epsilon naught. And then I can say this is the partial with respect to Z of this. I can rewrite as Z squared plus R squared to the 1/2 minus Z. That might make it easier to see. And now we can say this is negative sigma over 2 epsilon naught. The derivative of the first part is going to be 1/2 times Z squared plus R squared to the negative 1/2 power, and then times the derivative of the argument inside, or applying the chain rule, would give me times 2Z. And now I'm done with this part, minus the derivative of Z with respect to Z is 1. And now if I simplify this a little bit, I get minus Z over 2 epsilon naught. This will be 1 over 2 times the square root of Z squared plus R squared times 2Z, so the 2Z can go up there, minus 1. And now the last thing I can do is simplify. These 2's cancel, and if I multiply this negative through, I get sigma over 2 epsilon naught times 1 minus Z over the square root of Z squared plus R squared.